So you're now familiar with the fact that a point charge has an electric potential that varies inversely with the distance from that point charge. If we look at electric field lines of this point charge, we know that for this positive point charge, the electric field lines point radially away. We also know that equipotential surfaces are centered on that source charge. So these are concentric spheres all centered on the source charge. Well, there's one thing I want you to notice about the relationship between the electric field and these equipotential surfaces. Notice how electric field lines are perpendicular to each equipotential surface. And that's the nature of the electric field and equipotential surfaces. Field lines cross equipotential surfaces at 90 degrees. Very important point to remember. An electric field line will cross an equipotential surface at 90 degrees. In other words, an electric field line is perpendicular to equipotential surfaces. Another thing I want you to note, based off of our previous examples, notice how I drew and indicated the electric potential as decreasing with distance. And notice that the electric field lines point in the direction of decreasing electric potential. So that's a very important point, that an E field line indicates the direction of decreasing electric potential. Now, because electric potential is defined as electric potential energy per unit charge, we can equivalently say an electric field line indicates the direction of decreasing electric potential energy. Just remember, though, that there is a difference between when we say electric potential and electric potential energy. Electric potential energy is an energy shared between two charges, while electric potential is the ability of a single source charge to give another charge potential energy. You don't need another charge in the field for a source charge to have electric potential. It is the measure of the potential energy per unit charge. So when we say that an E field indicates the direction of decreasing electric potential, we could equivalently say it indicates the direction of decreasing electric potential energy. So I'll just say in parentheses, or potential energy. This means that in the absence of other forces other than the force due to an electric field, a positive charge will accelerate from high to low electric potential. While a negative charge behaves just the opposite. A negative charge, and it looks like I forgot to put a word up here. I'll insert charge right there. A negative charge will accelerate from, here's the thing, it's the opposite, from low to high electric potential. So what does this mean? Well, it means that if we had two charges, we'll say we have a positive charge right here and a negative charge right here. Well, the positive charge will accelerate from high to low potential, so that positive charge will begin moving away from the other positive charge, while the negative charge will move towards the other positive charge. Negative charges always behave opposite to positive charges. Let's replace this positive charge with a negative charge. For negative charges, the electric field lines point inward toward that negative charge. And we know that electric field lines point from low, and we know that electric field lines point from high to low potential. We should also note that positive charges are sources of positive electric potential. While negative charges are sources of negative electric potential. So this sketch depicting a negative charge is a source of negative electric potential, and we know electric field lines point in the direction of high potential to low potential. So I am going to insert a minus sign in front of each of these values that I copied from our positive source charge. Notice that as we go from the outside to the inside to the center of the circle where the charge is located, notice how the electric potential surfaces become more and more negative. And remember, a negative number with a larger magnitude is actually smaller than a negative number with a lower magnitude. For example, minus 100 volts is a smaller value than minus 35 volts, just like minus 1 volt is smaller than 0 volts. So this is indicating the direction of decreasing electric potential. And that's how the electric field lines orient. And again, in this illustration, if we were to take a positive charge, and let's say we were to place that positive charge right here, and we were to take a negative charge and were to place it right here, remember, positive charge will accelerate in the absence of other conservative fields and external forces. A positive charge will accelerate from high electric potential to lower electric potential, while negative charges accelerate from lower potential to higher potential. And that makes sense because opposite charges attract, like charges repel. Positive charges will accelerate towards that negative charge, and the negative charge will accelerate away from the other negative charge. This is a relationship between an electric field, electric potential, and the charges involved.